All right, everyone. So as you guys settle down, I'll just make a couple of brief comments about the example that Dr. Liu did last time. Basically on the torsion problem. This was the problem that you all solved last time. So overall, I think um, hopefully you all understood where all these shear, bending, and torsion diagrams are coming from. But I just wanted to emphasize certain points here. Um, I think the way to visualize this problem really is that if you look at these two legs of this frame, these two legs really just act like cantilever beams. This guy bending down this way, and this one bending up the other way. And there's a jump in the bending moment diagram here. Anybody, any ideas why there's a jump in the bending moment diagram? When do we have a jump in the bending moment diagram of a beam? When there's a concentrated moment at that location, right? So if there's a concentrated moment at some point in the beam, then there's a jump. Is there a concentrated moment at the center of this beam? Right. So that concentrated moment really is coming from that torsion in the rod AB. So whatever bending moment this member BC had accrued up until point B, and the same thing for BD, it jumps because all of that bending moment gets converted to the torsion in member AB. So that was one point. Another couple of good questions that came up last time was um, why did we apply P prime and P prime, two P primes here? Because normally in virtual work, in the virtual work method, you apply P prime where you want the displacement. And indeed, if you do it that way, you would still get the same result, as Dr. Liu pointed out. But if you apply only one P prime, do you think your bending moment diagrams, shear force, and torsion diagrams, would they be simpler or would they be more complicated? Right. So if you just apply one P prime, you can get the right answer, but the diagrams that you will end up getting would be much more complicated and certainly different from the real force diagrams, right? Because the benefit of applying both P prime and P prime opposite in the same way that the real loads were applied is the main benefit is that you don't have to redraw the shear force, bending moment, and torsion diagrams. You can take the real diagrams, scale them to get the new virtual diagrams, right? And after that point, I think it's mostly algebra, but the key point always is how to set up these integrals in a virtual work method. It's always shear stress multiplied by shear strain, of course, the kappa factor, and the stress. Maybe I should write it as divided by A and then A here, which gets cancelled out. So always it's virtual stress times real strain for shear, for bending, and for torsion. And if you sum that all up, you should get the result for no matter how complicated the real problem is. So just wanted to make that one comment. Any particular questions on this example? Go ahead, Frederick.
Would you mind going over the brief
The, that was basically one leg here. So it would the bending moment, shear force diagrams, and so shear force would be like this. There would there be a shear force? I'm not going to go through it in detail, but just because I want to move on to this new topic. But I think you will see that there will be a shear force going through this member as well. There would be a bending moment here. There would be a bending moment here as well, right? And torsion, there would be only torsion in this member. So essentially the idea is very similar to this problem, but the bending moment, shear force diagrams and torsion diagrams are slightly more complicated in that case because it won't be a symmetrical structure in that case. So just because this was a symmetrical structure, the diagrams were a little bit simpler. Okay, but I can certainly make an example out of that, and I can post it, add to the lecture notes, and you can review it in much more detail. Okay. All right. So let's jump into the material for today. We're going to switch gears a little bit, and we're going to talk still about energy methods, but on a different topic that is related to using minimization principles to try to find deflections. Okay. So till now, what we were doing was using conservation of energy. In the first case, we were using real work, real energy. We are saying that the external work done is equal to the internal energy stored, and therefore we can find some unknown displacements. But now we are going to do something slightly different. We are going to say that in order for a structure to be in equilibrium, it must try to minimize its energy. And I'll make more precise statements in a little bit. So this topic is very related to the virtual work method. In fact, if you'll see that almost all of the calculations turn out to be exactly the same as the virtual work method, but conceptually it's very different. And let's see what this principle first of all says. So what we are going to talk about rests on something called this principle of stationary or extremum potential energy. So for structures, if you have a beam or a truss or any building, a bridge, whatever, if you apply loads, they of course deflect. And what we are going to say, what we are saying in this theorem or in this principle really is that the energy stored in the structure has to be minimum to be, maybe I shouldn't say stored in the structure. The energy of the system has to be minimum in order for it to be in a equilibrium configuration. So let me first of all clearly read this, because it's a kind of a tricky statement here. So given a structure, loads, boundary conditions, and all of that, you have to first consider a set of possibly infinitely many kinematically admissible deformed configurations. So let me try to explain that phrase first. Here's an example. I have a cantilever beam, an end support, and I have a load applied in the middle. So under the action of this load, there are many different possible configurations or deformed configurations that the beam could take. I have fixed at this end, roller support here, and I'm applying a load here. So most likely you would expect this to be some sort of a deformed configuration. But there are infinitely many kinematically admissible configurations. What does that mean? As long as I'm not violating any kinematic conditions. What are kinematic conditions? Kinematic conditions simply mean that as long as the beam is continuous, as long as there are no sharp corners in the deformed shapes of place, as long as I'm not violating the support conditions either on the right or on the left, then it's a kinematically admissible configuration, right? So for example here, in this case, this beam curving upwards, going back to the displacement 0, even though we know that this won't be the likely deformed shape for a vertical load applied here, this is a kinematically admissible configuration. Similarly, this guy, S-shaped, is also a kinematically admissible configuration. And a likely deformed shape, which is this, is also, of course, kinematically admissible. What is not kinematically admissible is this. So maybe I'll write that here. Not kinematically admissible. And the figure on the right is admissible. So you can imagine that given a structure, given load, given boundary conditions, there are really infinitely many possible configurations that the structure could take, right? And what this principle says is that among all of those infinitely many possible configurations, the actual deformed shape is the configuration that extremizes. It could be minimizing or maximizing, and I'll talk about that also in a little bit, usually minimizing, that minimizes the total potential energy of the system. So in this case, when I have a structure, when I'm applying a load, the actual deformed configuration is the one that minimizes the total potential energy of the system. That includes the internal energy stored in the structure and the external work done by the force. Okay, so that's just a principle. There's no proof, or there's no this is a theorem, just like Newton's laws. There's a law. This is a law. Okay, so we have to accept this as an axiom. And if we do that, then we can see. I'll show you in a little bit that we can derive a lot of interesting expressions that allow us to solve displacements and forces and so on. So here's a very simple analogy of what this principle is and how does it relate to what we have learned until now. So what we have learned until now is basically the Newtonian mechanics approach, which is basically saying if I have a mass or if I have any structure, I can draw free body diagrams in force equilibrium to find out my displacements, and that's what we've been doing till now. So, for example, a mass hanging from a spring, I want to find the displacement. The first thing I do is draw a free body diagram. I have that mass mg pointing downwards, and if I have a displacement of d, then kd would be the spring force pointing upwards. And equilibrium simply means that mg has to be equal to kd, and very simply I can evaluate that kd is or the displacement d should be equal to mg divided by k. No surprises there. That's pretty trivial. That's what we've been doing in Newtonian mechanics, right? Now, on the other side of this approach is the principle that I just talked about, the principle of stationary potential energy. Here, we are not going to make use of any Newton's laws or equilibrium or anything. We'll just simply use this principle that minimum potential energy of the system is the equilibrium configuration, and let's see if we come up with the same result. Okay, so in this case, we are saying that the total potential energy pi is equal to the internal energy stored in the structure plus the potential due to external forces. So this is not just the work done, this is the potential change in potential due to external forces. So let me see if I can explain that a little bit. First, let me talk about internal energy. If I have a spring, if I give it a displacement d, what is the internal energy stored in that spring? Um, yeah, internal energy stored in a spring, if I give it a displacement delta, right? Force is equal to k times delta, and long back we had derived it as half times k delta square, right? Half k delta square is the energy stored uh, in the spring. And let me ask you this: the potential due to external forces, the only external force in this case is the gravity. And if this mass moves down by an amount d, does the potential energy increase or decrease? Decreases. By how much? mgd, and negative sign, right? So I'll write that. So plus negative mgd. The first term is just the change in or the increase in the internal energy of the spring, and the second term is the change in the potential energy of the mass. Those are the only two things. Now I'm going to say that for this to be in equilibrium, this energy term has to be minimum. And minimum means I need to, of course, take derivative of this guy with respect to d. And we clearly get this is equal to half and 2 cancel off. I get kd minus mg equal to 0. And once again, I'm back to the equilibrium equation. But the key point to notice here is that on the right-hand side approach, I did not make use of Newton's laws or equilibrium or anything. Equilibrium and Newton's laws were the consequence of this principle, right? So just minimizing or extremizing the total potential energy of a system gave me the equilibrium configuration. So somebody might ask, well, that means that is that more fundamental, or are Newton's laws more fundamental? And really, there's no answer to that. That's the chicken and egg problem. They both are independent concepts, and they both can you can derive the other one from one of them. Okay, so these are two parallel sort of approaches which can allow you to find deformations or displacements in your structures. Okay, here's a little bit about why I was saying extremum, not necessarily minimum. Okay, um, we know that if we take the second derivative of our potential energy, right? If we take the second derivative of the potential energy and it comes out to be positive, what does that mean? Second derivative. Okay, so if I give you a function f, I ask you to find where does this function f go to minimum or maximum. Okay, so to find the minimum or maximum, you would take the derivative like we just did. Now, to find whether it's a minimum or whether it's a maximum, what would you do? You would take the second derivative, right? So the second derivative, when it is greater than 0, what we see is that what we will have is a minimum potential energy, which means um, stable equilibrium. And in the other case, if we have second derivative, which is a maximum, this ball resting on a curved surface is also in equilibrium. They're both in equilibrium, but one is a stable equilibrium because if you shift the ball a little bit, it comes back to its original stable equilibrium position. In the other case, it's an unstable equilibrium because if you shift the ball, of course, it falls off. So equilibrium by itself does not mean that the structure is stable or unstable. Equilibrium is just equilibrium, meaning sum of forces is equal to 0, or that the potential energy is being extremized, either maximum or minimum. It's the second derivative test that tells us whether it's a stable equilibrium or it's an unstable equilibrium. And this is another benefit of this energy approach. With the Newtonian or the Newton's laws approach, you don't really have a measure of energy. Yes, you can find it, but you would have to do extra work to do that. In this, in the energy approach, you automatically get a measure of whether the equilibrium that you have is stable or unstable. A very simple example that is actually more practical that you might relate to. If I have a column, if I apply a small load on top of it, there's going to be some axial deformation, maybe some bending also, but uh, there would be a point up until which this column would be able to take that load, no problems, right? Now, now let's imagine that this column remains perfectly straight, and if I keep on increasing the vertical load on top of this column, there will come a point at which, if the column is still in equilibrium, it remains perfectly straight, but that equilibrium is unstable. Even a slight imperfection, and that column is going to buckle out of stability, buckle out of plumb. Okay, and that's really a stability problem. So um, um, for small forces, the column remains stable, and then if I increase the forces, if we load up our buildings enough, the columns would go unstable. Okay. All right. So without going into too much detail about how to calculate deflections using this method, we are going to make use of this principle to derive, or not derive, but to talk about a couple of theorems that structural engineers devised. Um, so one of the one of the theorems that an Italian structural engineer, or actually a railroad engineer, devised is the person by the name of Castigliano. Anybody heard of this name before? No? Okay, so Castigliano came up with two theorems, and later on, people showed that these theorems were really a consequence of the principle that we just talked about, the principle of stationary potential energy. But at that time, these were quite innovative theorems. So in the first theorem, um, Castigliano said that for an elastic structure, it could be linear or non-linear. By the way, that reminds me, Can an elastic structure be nonlinear? Can an elastic structure be nonlinear? What would that look like if it were an elastic structure and nonlinear? So if I, for example, a spring is, well, assuming that there is no plasticity going on in the spring, so it remains elastic. If I apply a load P, it compresses by some amount. If I apply load 2P, it does not compress by 2 delta. It compresses by something else. So, for example, a simple depiction of a elastic non-linear system. Well, let me first draw linear elastic system. This is linear elastic, right? You give me this is delta and this is P. You apply some load P, I get some delta. I apply 2P, I get 2 delta. On the other hand, a non-linear elastic structure would be something like this. The key thing about elasticity is that when you load it up this way, unloading also occurs along that same path. So as long as after removal of the load it comes back to zero, it's an elastic structure. But it's a non-linearly elastic structure in this particular blue curve. And inelastic structures are structures where we have plasticity. So for example here, and then when I unload, it does not come back to the original point. So that's a plastic structure where there is some dissipation. So let's go back to this. So we're talking about elastic structures, could be linear or non-linear, with constant temperature, rigid supports, and so on. Basically talking about a conservative system. The first theorem says that if I take the derivative of the internal energy with respect to a particular displacement in the structure, then that would be equal to the force applied. So if I have an unknown force in a structure, I want to find some unknown force in a structure, like a reaction or some internal force, then I can use this theorem to find that force. But let's see how this even works, whether how we can derive this. So the idea here is that originally I had this structure with this black outline. There were no forces on it. There is some boundary condition, some region where it is fixed. And then I applied some real loads to it, P1, P2, P3, Pn, however many loads you want. And what we are saying is that if I change the displacement of one of those loads while keeping the displacement of all of the other loads the same, right? So I'm not changing the displacement of any other point of load. So if you look at this blue line, that's the deformed shape, and the dotted blue line is the shape that I get after I increase one of those displacements while keeping all the other same. So in doing that, I will do some external work. That external work would be equal to what? That external work would be equal to, in this case, half P3 delta 3 or P3 times delta 3. Half would be the work done from going from black to this solid blue, right? Because there I'm applying the load slowly. So when it deforms through this, then the work done would be half P3 times delta 3. In what I'm doing now is I'm changing the displacement of this point while P3 is already applied. So since P3 has already been applied, it remains there, and the work done here is actually equal to making sure that is this area right here. So assuming that this is P3 and delta 3, the area is this area right here, which I will write as Pi delta di plus half times dpi times delta di. Right? So all that this is the area of going area under the P delta curve going from delta I to delta I plus d delta I. And if you look at that small triangle up there, the area of that small triangle in comparison to the area of this rectangle is negligible. So I'll assume that the second term in here is 0. Okay. And the remaining external work would just get stored as internal energy in the system. So if this was external work, that also is the internal energy stored in the system. Okay. Let me ask you this. Do any of the other forces do work? Why did I not account for P1, P2, Pn, and so on? Correct. We are saying that we're going to move delta D3 in this case, or delta I, while keeping the displacements of all the other loads constant. Okay, so that's why all the other forces don't do any work. And after this point, it's a simple shifting d delta I to the other side and taking derivatives. So we get dui dpi is equal to, sorry, not dpi, but d delta I is equal to pi. So that's the first theorem. And as I said, this theorem is helpful for us to find some reactions or some unknown internal forces. If there's an unknown internal force pi, I can use this to find it. But usually it's very complicated. And if we are trying to find deflections, this doesn't really help us. Okay. So here's sort of a quick example. If I have a truss structure which is fixed on two ends, I apply some load. I want to find what the internal changes in length of these or internal forces in these members are. The most straightforward way would be to use the Newton's approach, right? Draw free body diagram, find out the internal forces. But just to show you how it would work, you could apply this principle of stationary potential energy, write down the internal energy stored in the first member, the second member, and the change in the potential of the applied force. That would be ui, and taking derivatives of ui with respect to AB and with respect to AC, you could find the internal forces. Now in this, the key thing is being able to express delta y, the vertical displacement, in terms of delta AB and delta AC, which is not straightforward. But this is again something as an aside. It's not even in your books. I don't expect you to give any homework problems or quiz problems on this, but this is conceptually important to see what we are doing. Where does it fit in the energy methods? Okay, so the more important theorem for us will be this theorem 2. That really does allow us to calculate some unknown deflections in structures. So in this case, once again, if we are constraining ourselves to linear elastic structure, we are not getting into nonlinear structures in this case. So this second theorem is really much more restricted. So linear elastic structures with constant temperature and rigid supports, once again talking about conservative systems, we are saying that if we want to find an unknown displacement delta I, so I have a structure, some bunch of loads applied to it, I want to find the displacement at some point in the structure. What I can do is I can apply a fictitious, actually I shouldn't say fictitious, it's not a virtual load, it's a real load. I can apply a real extra real load pi on top of that, and what we are saying then is that the internal energy taken derivative with respect to that extra applied load would be equal to the displacement at that point in that same direction. And let's see how that works. So for this problem as well, we are going to make use of the conservation of energy approach. So if originally I had this black structure, when I applied these loads P1, P2, P3, and my, well, maybe not yet. So when I applied P1, P2, P3, what would be the total external work done in going from this black configuration to the blue configuration? I have a structure. I have applied P1, P2, P3, three loads on top of it. And slowly the structure deflects to this new position, this blue position. The corresponding displacements are delta 1, delta 2, delta 3. And what would be the total external work done during that deformation? Half, right? There has to be half this time. Half P1 delta 1. So, all right. So, sum over all the elements of half times P m times delta m. And not elements, but really these are the load points. So, and what we are going to do next is we are going to change or we are going to apply this external real load Pi at the point where we want to find a displacement. So if we do that, then the structure will store additional internal energy, and we can equate the change in energy to that change in external work, and we can find that unknown displacement. So in order to do that, let's go through a couple of steps. When I apply this external Pi, there will be change in the internal energy, right? Whatever internal energy I had here will change to ui plus dui. And I can use the chain rule to write an expression for this. Ui plus partial ui Pi, because that's the external, that's the changing force that I'm applying, times dpi. Is that, hopefully you all see that this is nothing but the chain rule. Ui is a function of all of these external loads. If I change one of the external loads, then the change in energy can be calculated with the chain rule. There are, of course, much other terms, but we are saying that all the other terms are constant in this process. So this was one way. In one case, we were finding out the change in energy by first applying the actual loads P1, P2, P3, and then varying the one of those loads Pi. In the second case, what I'll do is I'll first change the Pi load and then apply the actual loads. Will it matter, the final configuration or the internal energy stored? It doesn't, right? We also went through this argument long back when we were talking about two loads, P1, P2. Doesn't really matter in which order I apply P1 and P2. I could apply them both at the same time, or P1 first, P2 first, doesn't really matter. So in this case, what we'll do is we'll note that the change in energy can still be calculated by first applying dpi and then applying the actual loads. So in that case, all we need to do is to sum up the area under this triangle. So the first term is half times dpi d delta I, that's this red triangle below, plus we have dpi times delta I, that's this blue rectangle here. And then there's this last green triangle, which is, actually I should have written this guy also in green. So the original internal energy is what I'm writing in green. So plus half P I delta I. And there should be a sum here. Okay. Once again, this tiny red triangle is negligible in comparison to the other areas, so I'll straight away neglect that. We know from above, let me call that equation 1. We know from equation 1 that ui is equal to half p delta. So I can cancel off this ui and this half p delta from both sides. What we are left with is dui and dpi delta I. Just take dpi to the other side. And I think I've done that here. Um, Maybe I'll write that again. So dpi delta I and plus sigma half pi delta I. Once again, that I've already cancelled that term. And what we are left with then is that partial ui partial pi is equal to delta I. So both of these theorems rely upon these thought experiments by just taking a different set of sequences of loading up the structure and measuring the change in energy when we do that. And one of the theorems allows us to find unknown internal forces or unknown reactions. The second theorem is what we are going to use a lot more to find to find unknown displacements. Okay. Um, as a side note, this particular second theorem rests on what is called the principle of stationary complementary energy. Now, complementary energy is a completely fictitious concept. There is a real energy, but complementary energy is essentially the area of the triangle above the P delta curve. The area of the triangle below the P delta curve is the real energy or real work done, right? Complementary energy is area of the triangle above this P delta curve. And um, this particular theorem rests on the fact that not only is the real potential energy of the system minimized or extremized, the complementary energy can also lead. This principle of stationary complementary energy is what leads to this second theorem. The fact that we are talking about linear systems also is clear here. If the system is non-linear, then this complementary energy would not be equal to real energy, right? The fact that this system is linear means the area of this triangle would be equal to the area of this triangle. If the structure is non-linear, then the areas of the triangles won't be equal, and that's why the second theorem clearly says for a linear elastic structure um, we cannot tolerate non-linear structures here. So I think that's more and more quite a bit on the concepts. Let's take a look at some consequences of these two theorems. Okay. One of the consequences of this theorem is this theorem of least work. Um, so essentially, what this says is that for indeterminate structures, if there is a redundant reaction or a redundant internal force, we can find that um, by using this second theorem of Castigliano. So the redundant reaction for a statically indeterminate structure are such that they make the internal energy a minimum. Here's this example, and normally what we would do is to remove this support, apply some By here, and we would use compatibility then to find this By. Right? That would be the normal approach that hopefully you all have seen in 371, and again you'll see quite a bit of that in this course later on. But if we use this Castigliano's second theorem, we can express the internal energy stored in the beam in terms of this unknown reaction force By and take the derivative of that internal energy with respect to By and set it equal to 0 because we want delta B at this point to be equal to 0. Right? So when we take the derivative of energy with respect to a force, set it equal to 0, we are minimizing the energy with respect to that force. And that's why this is called the theorem of least work. So let's see how that works. Um, um, you should all be able to see that under the action of this By and this P, the bending moment diagram looks like this, and essentially actually it looks like all the way up here and then goes down to some point here. But I'm going deliberately writing them in or drawing that in two different curves, because that will be easier to integrate. Okay, so if I write x here, what would be the internal energy stored in the beam? If this is the bending moment diagram, what would be Ui in this beam for some load By here and some force P here, for which the bending moment diagram looks like this? Maybe I'll write the expressions as well. So going from the right, the positive bending moment is By times x. And what would be the expression for this bottom curve? P times x minus L over 2, right? Because, right, minus P times x minus L over 2. So we can check. Of course, it goes to 0 here. And when we have L here, we have the moment, correct moment minus PL over 2. So internal energy is simply half m as a function of x squared over EI dx over the entire length, right? And we can split that up into two integrals, 0 to L over 2, and I have a By times x there, whole squared, 1 over 2 EI dx, and plus a second integral going from L over 2 to L of what? I would need to add these two, right? So I would do By times x minus P times x minus L over 2, and there would be a square on the whole thing, right? And dx. So if I were to simplify this, what I would get is By minus P times x and plus PL over 2. That's the thing being squared. So I think the expressions turn out to be somewhat long, but 1 over EI By square, and we have integral x square dx between 0 to L over 2, and we have plus 1 over 2 EI I'll have to expand that as well. So 0 or L over 2 to L, By minus P square x square plus 2 By minus P x plus PL over 2 and dx. Okay. Clearly you can see that the internal energy Ui is a function of By. April? Say it again. Squared, right? Thank you. But once again, the point here is that internal energy is a function of that unknown force By that I'm trying to find. If you do all of these integrals, you will find that there's a sort of a long, complicated expression, but that can be taken derivative with respect to by easily. Set it equal to 0, and you'll be able to find by. So I'll let you complete this by yourself, but you should be able to get back to exactly the same thing that that you might have seen in examples before. Okay, and but I guess another point that I want to make here is application of this theorem or these Castigliano's theorems to find unknown forces really is quite complicated. Just like just like the principle of sorry, the first Castigliano's theorem, if you are able to express delta y in terms of the displacements of these two legs, that's a complicated geometry problem, right? In the same way, this corollary or the principle of theorem of least work to find By, the expressions can get quite tedious. And that's why we don't use neither the first theorem um, or this theorem corollary for the least work unless those expressions are really simple. But what we'll focus really on is this Castigliano's theorem, second theorem, as I mentioned. So this is one of the first examples that I'll need that you will need to solve homework problems and quiz problems on. Um, so if we have a truss problem, and if you are if you need to find displacement at some point, for example, this three-bay truss, where I need to find the displacement at delta E, then we will use this second theorem of Castigliano to find that displacement. So once again, um, if I write the internal energy stored in the truss under the action of all of these forces, okay, um, that would be sum over all the elements of the truss half times Nm, which is actually a function of this Pi force. So when I write Nm brackets Pi, that's a single quantity. That's not, so it's a function of Pi, because as I change Pi, the internal forces in the truss would change. This N represents all the internal forces in the truss. Square and Lm over Ae. Right? That's the energy stored. Um, that's the energy stored in the structure. So we have real loads P1, P2, P3. We have an additional load which we will change uh, from Pi to dPi, and we'll try to find out the derivatives of that. So if we change that load dPi, then we are just taking the derivative of this expression, and we can do that by adopting the chain rule. So half derivative of something squared is twice Nm Pi, and what next? Applying the chain rule, derivative of Nm and Pi with Pi equal to 0, and times whatever is remaining is Lm over Ae. Okay. So all I did here was applied the chain rule to take the derivative of ui. We get 2 here. Of course, that half and 2 cancel off. And what I'm left with is Nm as a function of Pi, but since we are finally going to set Pi equal to 0, therefore what we get is N times L over Ae. That should sound familiar. And I'll write that second. And I'll write this term Nm over derivative of Nm with Pi out here. So is equal to sum over the elements and partial Nm as a function of Pi, derivative Pi evaluated at Pi equal to 0, and something in blue that is NM LM over AE. So hopefully these two terms look familiar. This guy is nothing but the response of the truss to a supposed virtual force. And this right-hand side term is nothing but the real displacement. And that's why even for the Castigliano's second theorem, the calculations end up being exactly the same as the virtual work method. Okay, I guess that's a good indication that the lecture is over. Okay, so I'll see you all on Wednesday. Sorry? Yes, new homework will be posted 5 p.m. today.